All right, happy Thursday. We are Thursday, week 9. This is the last of the new material. We will have office hours on Tuesday of next week, and that'll be our regular office hours, not the weird time like last time. So it'll be 5:30 to 6:30 Tuesday night right here in our normal Zoom. We'll do office hours. You can just drop in if you have questions since our test opens on Tuesday, our final test. And it's not cumulative. I mean, some of the topics are obviously used and throughout the whole term, but it is just on chapters 8, 9, and 10. So it's not cumulative. It's just 8, 9, and 10 on test 3. So, and I believe in the material, the week 10 material, I think is where you can find your reviews. There's a pretty good PowerPoint right in week 10 that is a final review, and it's really good one to print off. It pretty much has everything you need. And I'll show you that at the end. So we're going to finish up with 10.2. We're going to test hypotheses about a population proportion. And 10.2 uses it's going to use p hat, so, and all of the stuff for proportions. 10.3, we're going to test hypotheses about the mean. So this is going to use our sigma sub x bar and all of that. And it's going to use the t values, kind of like we did, and I believe that was 9.2. So 10.3 goes along really well with 9.2. 10.2 goes along really well with 9.1. So that's where we are. That's what we're doing tonight. And I'm hoping this isn't too big of a stretch from where we were with confidence intervals. We will see how it goes. My computer just unplugged itself. There we go. So remember, point estimate, we take the number of successes and divide it by the sample size. So this is the same thing we've been doing for a while. So successes divided by sample size, and we're good right there. Also, remember that our standard deviation, when we're dealing with p hat, we use the square root of p times 1 minus p divided by n. And our mean that we're using is just going to be whatever the population proportion is. And generally, the population proportion is from like a previous study, or it is stated that this is the proportion, things like that. So, whatever the population proportion is, that is our mean. And whatever and then this is our standard deviation. Remember that our sample needs to be a simple random sample, that NP times 1 minus P needs to be greater than or equal to 10. That shows us that we are normally distributed, and our samples need to be independent of each other, which means that our sample size needs to be less than 5% of the population. So these are the things that we need to check. And on your test, sorry, on the test, you're going to have to show all of the steps for a hypothesis test, and I'm going to walk you through what that's going to look like. All right. So, as a reminder, a two-tailed test, we use a two-tailed test, and I think keeps unplugging. That's the magnetic ones. Two-tailed test is when you hear the word different. I'm going to put different right down here. This is just a reminder. We learned this on Tuesday. Different. I can't spell different. There we go. So we use the word different with a two-tailed test. A left-tailed test is going to be like less than. It might say has decreased. Just basically anything that means smaller. Right-tailed test, we'd hear greater than or increased or anything that's going to be bigger. So these are the ways that we structure our hypothesis tests. And our null hypothesis will always say equals. Always, always is equals. Our alternative hypothesis never says equals. It's either not equal to, less than, or greater than. But this number is the same on both of them. This part is the same. The only thing that changes is the symbol. So just the symbol changes. All right, you're going to be given the level of significance. The level of significance is that alpha that we've talked about before, and it is based on the seriousness of making a type 1 error. So don't even worry about that that's what it is. just remember you're given that level of significance, and that's your alpha. That's the alpha. And it's the same thing. It means the same thing as when we were using confidence intervals. So test statistic is the standard deviation. Actually, test statistic here, sorry about that. Test statistic is a z-score. So it's going to be your p hat minus the p naught divided by the standard deviation. So you're going to take your p hat that you've calculated based on your sample, subtract the p naught, which is that population proportion that we're using, and divide it by the standard deviation. This is called a test statistic. So this is what I showed you before when we create a confidence interval. We create a confidence interval, and the number of standard deviations away from the mean, that's the edges of my confidence interval. That number of standard deviations, that would be your critical value. That critical value, that's the same critical value that we were using for confidence intervals. It's the same thing. So the number of standard deviations we can be away from the mean and still be in that confidence interval is the critical value. The test statistic is the z-score of our sample. So we're comparing our test statistic to the critical value. That's what we're doing here. And so this is the test statistic. It's that z-score of our sample. That's what we are comparing to our critical value to determine whether we have evidence to reject our null hypothesis. And that's what we're doing here. Okay, so we could use table 5 will give us our critical value. That's the Z table. That will give us our critical value. You can also use inverse norm as long as you use it correctly. We'll do that in a little bit. So you can use the table 5. Let me jump to that table. So at the bottom of our table, we already looked at this one right here. Now we're going to look over here. The nice thing about this is it has our most common levels of significance, our most common alphas, and this gives us the critical values that we have. So for a left-tailed test, our critical value is always negative. For a right-tailed test, it's always positive. For a two-tailed test, we're going to use both the positive and the negative to compare to our test statistic. And the reason that these are different, like our left and right-tailed are just the same number, just positive and negative. Our two-tailed test is different because remember we have to cut that alpha in half because half of the area is above my region and half of the area is below my region. So it's really important to kind of pay attention to if you're cutting it in half or if you're keeping the whole alpha. So we cut it in half for two-tailed tests. Oh, I can't write that on there. All right, let me go back here. So I'm going to show this right here. So take a look. Cut alpha in half for two-tailed tests. We keep the alpha whole for left-tailed and right-tailed. And once again, remember that left-tailed critical value always negative. For a right-tailed, my critical value is always positive. There we go. Any questions? Are we okay? We're good? Okay. All right. So our classical approach, you're just going to compare the critical value with the test statistic. So if my test, so I'm gonna do a left-tailed test on my drawing. That's really ugly. Let's try this again. Okay. So I'm going to do a left-tailed test just because I don't know why. So my left-tailed test, I have a critical value that shows me how many standard deviations below the mean the edge of my confidence interval is. I'm going to just put a number here. Let's just say this is negative 2.15. It's just a random number I came up with in my head. It's not based on anything. I just made it up. So if this is my critical value, I'm going to put CV for critical value. Once I calculate my test statistic, I'm going to compare it to the critical value. So if my test statistic lands out here, so let's say it was negative 2.65. If it lands out there, I'm going to reject the null hypothesis. But if it lands in here, then like let's say that it was negative 2.01. I'm making up numbers here. So it's inside. It's not definitely closer to that line than my arrow is. Then I would fail to reject. So I'm just comparing it with that critical value. So if it's outside my confidence interval, then I'm going to reject the null. If it's inside, if it's closer to the mean than my confidence interval, then I'm going to fail to reject. Does that make sense? Okay, I'm gonna move on. So this is how so for the p-value approach, you're going to compute your test statistic, as we said. Then we're going to, it wants us to use the table to estimate our p-value, which obviously we can do that. Or you can use normal CDF to estimate your p-value once you have those z-scores. But instead, I'm going to give you a calculator function that's going to do that for you, and it's going to be much more accurate. I highly recommend, rather than using table 5 or any other calculator function, I have one specifically for hypothesis testing, and I'm going to give it to you in a minute. We're going to do some calculations on our own first, and then I'm going to give you that calculator function. So when you're doing p-values, just use your calculator. Trust me, just use your calculator for p-values. So we're going to jump into some math here in a second. This is basically what it says. So important here, the way that you can tell using the p-value if we reject the null is if our p-value is less than our alpha, we will reject the null hypothesis. So if my alpha, let's say that my alpha is 0.05, that occurs quite frequently. Let's say that my p-value was 0.025. That number is less than 0.05, so I would reject the null. Now, if my p-value, let's say that my p-value was 0.08, I would fail to reject because that is bigger than the 0.05. So you just compare that p-value to your alpha and you reject or fail to reject. Questions? All right. I know it's always easier when we're actually do the math. So in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. So we have a 2007 poll. We've already seen this one before. 1,010 adults nationwide, 525 said that they did not trust the media. We're going to look at a significance level of 0.05. We want to know if there's evidence to support the claim that the percentage of Americans do not trust the media fully and accurately has increased since 1995. So this right here, our P, the value that we're going to test against is going to be this 46% here. That's what we're testing against. So the first thing I'm going to look at is, do we have a random sample? We're assuming a random sample. I'm going to write all the steps here. Assuming, I'm going to write them up top because I need room. Assuming random. If it doesn't say it's random, we're just going to put that we're assuming random. Next thing I'm going to check, are they independent? So 1,010 is definitely less than 5% of the population of the United States. So I'm going to say that 1,010 is less than 0.05. Capital N means the population. So 1,010 is less than 0.05. Therefore, we have independence. The last thing we need to check is if NP times 1 minus P is greater than or equal to 10. So NP times 1 minus P, which looks like this. N is 1010 times 0.46 times 1 minus 0.46. I'm just going to put this in my calculator and get a number. Maybe. Okay, 1010.46. 1 minus 0.46. That is 250. 250.884, which is greater than or equal to 10. On your test, I want to see these things. Show me those. Show me that those are true, because on your test, it's going to say show every step of hypothesis testing. So I want to see these. It's 2 questions, one for proportion and one for mean. And you're going to show it on your work. You're going to show me every step of this on the handwritten work. So show me these 3 things. Then we're going to write our hypothesis test. So my H naught, P equals 0.46. This is true until we prove it isn't. So until we have evidence against it, this is true. My alternative hypothesis, I know I keep using A and our textbook uses 1. I think my open math uses A, and it doesn't matter. Either one is fine. So it says that they think it has increased. Therefore, this is a right-tailed test. So they say that P is greater than 0.46. Remember, I stated that this number is going to be the same for both of these. We just change the sign in the middle. Okay, this is good. We've got this. So I have that alpha equals 0.05, and we know this is a right-tailed test. So I'm going to bop on over to my critical values. So 0.05, a right-tailed test, my critical value is 1.645. So my Z sub alpha, oh, sorry, bopping back over here. My Z sub alpha is 1.645. This is the critical value. All right, this is what we are comparing against. We're going to compare our test statistic to this critical value. All right, so we've got all the preliminary stuff done here. So you're going to be able to use a calculator function, and so all of this stuff is the by hand stuff. So your next step, you can either do the math by hand to find your test statistic, or you can use your fancy calculator, but you're going to write down what you put in your calculator if you use the calculator. I'm going to do it by hand right now, but I'm going to show you the calculator function in a minute. So by hand, remember, it is P hat minus P divided by the square root of P times 1 minus P divided by N. Okay, let me actually show you the math. P hat, my P hat, let me math this out. 525 divided by 1010. So I have 0.5198 minus 0.46 divided by square root of my P 0.46, 1 minus 0.46 divided by 1010. This is a lot, but if you're really careful, you can put this whole thing into your calculator at once. If you're really careful with your parentheses, this entire thing can go in your calculator. I'm going to show you what it looks like rather than just tell you to be careful. I'll show you how I put this in my calculator. So let me bop on over to my calculator. All right, numerator has to have parentheses. Minus 0.46, then divided by square root Once again, my numerator is going to have parentheses. 0.46 times 1 minus 0.46. Now, I probably would just put 0.54 because I know that that's 1 minus 0.46, but for the purposes of this, I'm just going to leave it there. Divided by 10, 10. That's how I have the whole thing in my calculator. I'm going to hit enter. So my test statistic, right, I'm going to write this down before I bop back over. 3.813. Okay. So my test statistic is 3.813. Oh, okay. If I was to draw this, which you don't have to do this in your work, but I want to kind of give you an idea of what's going on. If I was to draw this right here in my mean is 0.46. My z-score tells me that the edge of my confidence interval is right here with a z-score of 1.645, because that's telling me that the edge of my confidence interval is 1.645 standard deviations away from the mean. My test statistic, this right here, has me way out here in the tail because that is very far to the right of that 1.645. It is so far to the right. So we clearly are outside of the outside of that region, the critical region there. We're outside of the good region where we can live happily and believe the 46%. So we are out in the wastelands out there. So therefore, we're going to reject the null hypothesis. So here's, I don't even know if I have room for it, but I'm going to try to write it in here. Here's what I would say. I would say, because remember I said that when you write your conclusion, I want you to reference why you are rejecting. I would say, since my test statistic, probably our test statistic, I think that would be better. Our test statistic is greater than the critical value we have sufficient evidence to show that, I'm not going to write all of this out because I don't have room. The adults that context, put the context in there so that the proportion of adults that believe that that do not trust the media. So the proportion of adults do not trust the media is greater than 46%. I'll put the 46%. Therefore, I'm going to push this up and see. Oh, cancel. Therefore, we reject. I'm going to write up the side, the null hypothesis. So I want to see the words reject the null hypothesis. Now, I don't even care if you're super like detailed like this. Even if you just tell me our test statistic is greater than our critical value, therefore we reject the null hypothesis, I'm going to give it to you because I just really want to see that you have the process. I'm not looking for pretty words, but if you just tell me our test statistic's greater than the critical value, therefore we reject the null hypothesis, 100% I'm giving you the points. All right, I'm going to bop over to the one that they do. So this is all the stuff I said, simple random sample, NP 1 minus P greater than or equal to 10, sample size less than 5%. Here's their math for the test statistic and the level of significance. And then, oh, we haven't done the p-value yet. Okay, though this is the classical approach. So they have, these words are perfect. Even though this isn't their conclusion is going to be a lot longer. But if you give me, if these are the words you write, I will give you credit for it. They give you, so the p-value approach. So I'm going to show you the calculator function so that, because I want to do that for the p-value. I'm trying to see if it's on my other screen. It's not. Okay. So let me show you the calculator function. The calculator function, I want to make sure I write it correctly. Our calculator function is 1 prop z test. You can find it in stat, then arrow over to tests, and then you're going to go to 1 prop z test. This is our calculator function. So this is where we're going to get all of our good information. Let me bop on over to the calculator and let's do this. So stat, go over to tests and down to 1 prop z test. This is 1 proportion z test and hit enter. So what this asks me for is our p naught, because this wants to know the what the population proportion is, or what proportion we're basing it on. This is asking us for our null hypothesis. So it's 0.46 is my null hypothesis. Our number of successes, I'm going to go back to the other screen on my thing here. The number of successes was 525, and our sample size is 1010. So this is the tricky part here. I frequently choose the wrong thing. Now, if you get a very, very large proportion, a very, very large p-value, you probably chose the wrong one. And I choose the wrong one at least half the time. So I think that my hypothesis is that we are greater than our p naught, or our population that were our original. We think it's greater than. So I think that this is the right one. So this is where we are, and I'm going to hit calculate. Yep, this is the right one. Okay. I can tell because this is really small. So this has a z-score. This z-score is our test statistic. This p hat right here, this is our p hat. It's exactly what we calculated. This is our proportion of the probability that we would get a sample that size if the proportion, true proportion was 46%. If the true proportion is 46%, we have almost a 0% chance of getting the sample that we have, of getting 525 successes. It's almost a 0% chance. Now I want to remind you, when I have an E negative number right here, this is scientific notation. This is saying 6.858 times 10 to the negative 5th power. So I'm going to write this down and then I'm going to show you what to do with it. I'm going to write it on my final page over here. So we have 6.8587. I'm just going to go that far. Jump back over. So this said E negative 5. This is telling you, this right here is telling you to move the decimal 5 places to the left. So make this a super small decimal. So 1, 2, 3, 4, 5, 0, 0, 0, 0. My decimal is now here. So this number is 0.123468587. This is a really small number. This is practically 0. There's practically a 0% chance of getting a sample like that if the true proportion was 46%. Have any questions? Okay, good. So if you were doing this, if you were on your test, if you're using your calculator, what I would like you to show me, I want you to write down, oh, I used the wrong one. I gotta go to the right one. I want you to write down what you put in this screen. This is what I would like you to write down. If you, instead of calculating the test statistic by hand, I would like you to write down these four, what you put in these four places. That's what I would like to see for your work. Write down one Prop Z test, then write down these four things. That's going to show me what you put in your calculator. You do not necessarily need to show me the output. If you want to write this output down, that's fine. You don't have to write down the output. You obviously are going to want to write down what, if you're using p-value, write down the p-value that you got. Or if you're using a test statistic, you're going to want to write that down. But you don't have to copy this whole screen. I'm okay with you just writing down the piece of information you pulled out. I'm allowing you on the test to use your own method. If you like the p-value method better, use that. If you like the test statistic method better, use that. But in this case, I'm going to pop back over. This number right here, woo, this number right here, this is our p-value. This p-value is definitely smaller than our alpha of 0.05. It is definitely smaller. Since that value is smaller than our alpha, we would reject the null hypothesis because that is smaller than 0.05 by a lot. But it doesn't matter. It could be, we could have gotten 0.046 and it's still smaller. So if it's smaller at all than our alpha, we reject the null hypothesis. Are we good? Okay. All right, so that's the end of 10.2. That's all we have to do with the proportions, so put that in your pocket. And we're going to move on to means. And this is going to have a different calculator function, equally as useful. Okay, so what we do with this is exactly the same thing we were doing with proportions. However, our test statistic, once again, it's going to be our X bar, so the mean of our sample, minus the mean that we're using for population, and divide it by this new standard deviation that we use for sampling distributions. So remember, the mean one is different. The mean one is different than the proportion one. When we are looking for critical values, as we did before, we're going to be using n-1 degrees of freedom, just like we did with 9.2. We'll be using our n-1 degrees of freedom for that. Okay. T-distribution, this is just a reminder. T-distributions are different for different degrees of freedom. It's centered about 0, symmetric. The area under a curve is 1, but it's kind of fatter in the tails than Z. I'm not going to ask you to tell me all of this. I'm just reminding you what T-distributions are. As our sample size increases, it becomes more and more normal. Bigger samples are better. Okay. So what we do when we test the hypothesis regarding the population mean. So simple random sample. I want to see this on your test. Simple random sample. The sample size I'm going to give you on your test is going to be less than 30, just letting you know. It's going to be small because I don't want to give you guys a huge number of numbers and have the chance of errors entering it in your calculator. I think it's only like 8 numbers. So you're going to have to just state that this is a smaller size. And I don't remember if I state that it's normally distributed or not. But if you just make a comment about how may not be normal or sample size is less than 30 or whatever, just make a comment about it. Still do all this math though. Just still do the math on it, but I just don't want to give you a super large sample size because you all know I typo in the calculator. If you're nervous about a test, you're more likely to typo in a calculator if you're putting 30 things in there. So I gave you a small sample size. So sample values are independent of each other. That's that 5% rule. the sample size is less than 5% of the population. Test those things. Make sure you state those things and move on. These are the same as before, except for we're using mu instead of proportion. And two-tailed, left-tailed, and right-tailed. These are the same thing. I know I'm whipping through these, but we've already gone over this, so I figure hopefully you'll slow me down if I'm going too fast. Okay, classical approach. So once again, I will give you the significance level. This is your test statistic. This is how you are calculating it, or you're going to use your calculator. We're going to use n-1 degrees of freedom for our critical value, just like we did previously. That's what we use to find the edges of our confidence interval. Same thing. It's all done exactly the same. Our two-tailed, we will cut alpha in half. Our left-tailed and right-tailed, that we will not cut alpha in half. And I think I called the wrong side critical region before. Critical region is the area you don't want things to land in if you're supporting your null hypothesis. The critical region is everything outside your confidence interval. I'm stressing that because I believe in quiz 7, you have to label where the critical region is. And this right here gives you a really great, a great visual of where the critical region is. Okay, classical approach, exactly the same as proportions. You compare the critical value with the test statistic. If your test statistic is outside of your confidence interval, you will reject the null hypothesis. If it's inside the confidence interval, we fail to reject. All right. We're going to use this says to use the table to approximate the p-value. Don't do it. Use your calculator. It is so much better. Do not use the table. It is a big pain in the rear. Use your calculator. P-value approach, same thing. If your p is less than alpha, if the p is less than alpha, we will fail to or we will reject the null hypothesis. So compare the p-value to your alpha. If it's less than alpha, the p is low, reject the ho. I know I'm whipping through these, but it's all the same stuff. I just said this. We are good. Okay. And this even says it. Use your calculator. See, it even says it right here. All right, let's do math. This says that this procedure is robust. Minor departures will not adversely affect the results. It says don't use it for small samples or outliers, but as I said, still use it. Make a note that your sample size is small, but still do the math. Okay. Yay, we get to do the math. What I don't like is that there's not a whole lot of room for me to do math here. So we're assuming the resting metabolic rate of a healthy male's in complete silence is 5710 kilojoules a day. One of the nice thing about having so many people going into medical fields in my class is I had asked one time what a KJ was, and they told me it's kilojoules. So now I know. So I've learned from my students. Researchers measured the RMR of 45 healthy males. This is my sample size, who were listening to calm classical music and found the mean RMR to be 5708.07 with a standard deviation of 992.05. At a 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than the 5710 kilojoules a day? All right, so different. It's a two-tailed test. So we are assuming that this is a random sample, assuming random. Assume random sample. Okay, that's lovely. All right. 45 is definitely, 45 is less than 0.05% of our population, obviously. There are definitely more than 45 healthy males in the US. Um, so yeah, it is less than 5% of our population. Lastly, my sample size greater than 30. You could just say n, small n is greater than or equal to 30. That's fine. If it's not greater than or equal to 30, if it states that it comes from a normal if the population is normally distributed, then you don't have to have a sample size greater than 30. That's what I'm trying to remember if the test question says it is normally distributed or not. I can't remember. And I might add that in if I haven't already. So remember that if it states that the population is normally distributed, the sample size doesn't have to be greater than 30. That only has to be greater than 30 if we don't know that it's normally distributed or if it isn't normally distributed. Make sense? Okay, so let's take a look at, we have a mean, or I'm gonna write my null and alternative hypothesis. I'm gonna write it over here on the side because I need the room at the bottom for math. My null hypothesis is that the mean is 5710 kilojoules. It's kilojoules per day, but I can't really fit that. My alternative hypothesis is that my mean is different than 5710 kilojoules per day. So there's my null and my alternative hypothesis. I'm going to cut the alpha in half. I'm going to cut this in half for my when I look for my t-value. So I'm going to use alpha divided by 2 is 0.025. Now we're going to use n minus 1 degrees of freedom. I'm going to pop over to my t table. So the thing is, I don't have n minus 1 degrees of freedom or 0.025. Where are we? Okay. So a couple of things we can do. We could either take these two numbers right here and find the value halfway between them. You can just take 22.021, let's see here, 2.021 plus 2.009 and then divide it by 2. It gives me 2.015. I'm going to write this down just a second here. My t sub alpha divided by 2. I'm going to write this down and then I'm going to use my calculator, the inverse t, to see how close it gets me. So let's check it out. So second vars inverse t, with it, we have 0.025, sorry, 44, because that's n minus 1 degrees of freedom. Hit enter. That's lovely. 2.015. That's exactly what we got dividing it in half. I love it when the numbers work. So this gives me negative, which is fine. We just have to, we're always going to get negative when we use inverse t with our alpha. You just have to remember, left-tailed is negative, right-tailed is positive, two-tail, you use both. So here, I already wrote it down. I'm going to put a plus or minus here. Plus or minus. Okay. So I believe I mentioned this before. Remember when we talked about this? This was a while ago, chapter 7, I think. So it's been a while, maybe 8. When I talked about if the number that we are looking at is smaller, then we're looking at less than. If it's smaller than the original value, the original mean, we go less than. If it is larger than the original mean, it's going to be greater than. This number is smaller than 5710, so my test statistic is going to be a negative z-score. Therefore, we're going to be looking at the negative of our critical value. Does that make sense? Okay, so let's math this out. I think you probably could look at this and see that my z-score is probably not going to be very high, especially with this being a standard deviation. It's not going to be very high. I can pretty much guess we're going to fail to reject, but I don't know absolutely sure. So here we go. So I take that's going to be x bar minus mu divided by s divided by the square root of n. So it's going to look like this, x bar 5708.07 minus 5710 over 992 divided by the square root of 45. This is really ugly and it's going to require a lot of parentheses, but you still can put this whole thing in your calculator if you're very careful. I'm going to pop over to my calculator. Okay. Parenthesis. My numerator needs parentheses. 5708.07 minus 5710. Close those parentheses. Divided by parentheses 992 divided by square root of 45. And then I have to arrow out. You need to arrow out of your radical and then close the parentheses. So this z-score, or t-score, sorry, is negative 0.013. That makes sense? Good so far? Okay. So coming back over here, if I'm comparing, so I'm going to draw the picture. Here's my picture. So my mean is right here. This is 5710. And I have z-scores or t-scores going both directions, 2.015, negative 2.015. It goes all the way out to these lines. It's clear that my test statistic right there is barely below. It's right here, barely below that mean. It is inside the safe region. It is inside the confidence interval. Therefore, I'm going to fail to reject. Once again, I don't have a whole lot of room, so I'm going to do the best I can. Since the test statistic of negative 0.013 is greater than the critical value of negative 2.015, we fail to reject. And since we don't have a lot of room, I'm going to put H naught right there. Questions? All right. I'm going to give it a second for those watching to write things down. Okay. Obviously, this is all going to be right here. So did they do it? Did they test these things? Sample size is large. It doesn't say the rest of the stuff, but we're going to call it good. This shows my level of significance, my sample mean, my standard deviation. It shows my test statistic, which is the same thing that we got. It's a two-tailed test with n minus 1. They must have just grabbed the 40 because this is what the 40 was. So since 44 was closer to 40, they just grabbed 40. See, it works with 40 also, I guess. I personally just rather use inverse t or go halfway in between. I like accuracy. So since the test statistic is between the critical values, you could say it that way, we fail to reject the null hypothesis. You write these words or you write the words I wrote them, either way, you're going to get full credit on that. I believe that I have one for p-value approach. We're going to talk about p-value in a second because I think I have one. Yes, I have one with data. And we're going to put this one in our calculator. I'm going to put this data in the calculator. I'm going to show you the calculator function. And it'll be really nice because I'm going to be able to, I hate this term, kill two birds with one stone. So, but first we have 18 state quarters. It does not say that it is from a normal distribution. Now, what they really want you to do is they want you to graph it and show that, you know, where it says draw. Have you seen that in the bottom things where it says draw? It wants you to draw it. But we're just going to say that, you know, we're assuming that this is a normal distribution. We're just going to call it that. I'm not super concerned about it. I am concerned that this is less than 5% of the population, which it absolutely is. So the United States Mint says that 5.67 grams is the average. We do not know our standard deviation yet. The calculator is going to do that for us. So the calculator function we are going to use is you're going to go to stat, tests, and then t-test. That's the calculator function that we're going to use. Let's pop over here, clear this out. We're going to go in and put these numbers in my L1 list. Clear. What? Clear, enter. I don't know what I'm doing. I'm having issues. Clear, enter. There we go. Okay, I'm just going to enter these in. It's going to take a moment. I meant to actually put these in before we got here, but tell you the truth, I lost my cat and I was almost late for class because I couldn't find my cat. She was locked in a bedroom. She does that frequently. And I think I just messed up here. Oh, yeah, I did. She'll like go into a bedroom and hide. And then I don't know where she is because and I go to work and figure out that she's hidden somewhere. She's super dramatic about it too. I probably have too many in here. I think I did something wrong. We'll see. I'll look over them after I'm done. Uh-oh. A lot of 5.7s. Okay, well, it says it's 18. I'm just going to look at them real quick, make sure I have them correct. Okay. All right, they look good. Okay, now that those are in there, we're going to go to stat, over to tests, down to t-test. It's the number 2. Okay, so as we did with the confidence intervals, if you have the information, if you already have um, your X bar and your standard deviation and your sample size, if you're given all that information and you don't have data, like our first example, where we're given information, we didn't have data, we just put that in here. But we have data, so I'm going to go to the data screen. And this is going to pull it from L1. This mu naught, though, right here, we don't know that information. I mean, the calculator doesn't know that information. We have to put that in. It's funny that it's already in there. So 5.67 is the weight that we were given from the United States Mint. So you're going to have to put that mu naught in there. This is what we have with our null hypothesis, which I didn't write down. Sorry about that. So our null hypothesis, this is what we write down. List 1 is where our data is. Frequency always stays 1. This is a does not equal because it says different. that is there evidence to conclude the state quarters have a weight different than 5.6 grams? So this one is not equal to. See this draw right here? This draw is what would tell me if I'm normally distributed, but I don't even want to deal with that. So I'm going to hit calculate. So this gives me my X bar. So this is the average of all the numbers I put in there. This is the standard deviation of all the numbers I put in there. And this right here is my p-value. So first thing I'm going to look at is my test statistic is 2.75. We notice that it does not give me the critical value. We're going to have to find that. My p-value, I did things kind of backwards order, but it's going to be okay. My p-value, 0.014. I'm just going to write this down and pop it back over to my tables. Okay. Our significance level, I'm going to pop away. I got to go back here. Our significance level is 0.05. But as we dealt with this before, because it is a two-tailed test, we're going to cut that in half. So I'm looking at alpha divided by 2. It's going to be 0.025. So this is what I'm looking for. And my n minus 1 is going to be 17 because I have 18 as my sample size. So here we go. So 0.025 is right here. Let's go down to 17. 17 is right here. It's 2.110. So my critical value is 2.110. All right. Let's go back over here. I know there's been a lot of information. So critical value is 2.110. So here I'm going to draw this because it helps. Okay. So my mean, what was my mean? Well, my mean, they're saying it's 5.67. And then the critical value is 2.110 that way, negative 2.110 that way. My t-value, my test statistic, is 2.75. It is out here in the critical region. Since it is beyond the edges of my confidence interval, we are going to reject the null hypothesis. Or take a look at the p-value right here. This p-value is less than that 5%. Therefore, we're going to reject the null hypothesis because the p-value is less than my alpha of 5%, so or 0.05. I'm going to reject the null hypothesis. So you could state your conclusion either way. Is it over here? Yes. So you would either say, since my p-value of 0.014 is less than alpha of 0.05, we reject the null hypothesis. Or you can say, my test statistic of 2.75 is greater than the critical value of 2.110, therefore I reject the null hypothesis. Questions? All right. So this right here shows that they want us to verify there are no outliers. I'm not even going to get into that. I'm not making you guys do that. You're just going to make a statement recognizing that it's a small value, and then you're going to move on and just do the math. If I put this in my calculator, I think I have a screen for that. So notice right here, it's all like the line of best fit, and I don't even know why it's using a line of best fit. But if I put it into like there you go. So take a look at my bar graph. There's no outliers there. It's pretty symmetric. So I can graph it as a bar graph and say, oh yeah, that's fairly symmetric. But I'm not asking you guys to do that. We're just going to just make a statement about the small sample size. and then just move on. What I didn't write back here because I neglected to do that, my null hypothesis would look like this. Mu equals 5.67 grams. Then my alternative hypothesis would be mu does not equal 5.67 grams. Sorry, I didn't do all of that stuff. I get excited sometimes and I just want to jump into the math. You know me. This is how I am. All right. So are we feeling okay? Feeling like we can do this? Okay. I don't know what all my other screens are. We will find out. Okay. So they mapped it out here. They got the same test statistic we did and all the beauty right there. They rejected their null hypothesis. If you wrote this, exactly this right here, I would be happy. This is what you would write for your conclusion. Happy with that. I'm not asking you to get super fancy with your conclusions. I just want to know you know what you're talking about, that you know why you rejected the null hypothesis or failed to reject it. That's all I'm asking from you. So p-value, see, they even say t-test on calculator. Use t-test, get your p-value. So right here, you can say this. The p-value is less than the level of significance. We reject the null hypothesis. I want to see the words reject or do not reject or fail to reject. I want to see those words. Please be very, very clear about whether or not you're rejecting the null hypothesis. Pretend that I don't know what I'm talking about, and I want very clear you tell me that that null hypothesis is no good or that we're just going to hang on to it. So just pretend that you really need to be crystal clear. I want to know you know what you're talking about. All right. And then they get a little fancier than we do. Okay, this is all I have. This is the last of this. This is the last of all of the material for the entire class. How crazy is that? Super crazy. Are there any questions you'd like to ask on the recording? All right. Get off the recording.